So hello everyone, welcome you all to live session 11 of NPTEL course of Fluid Flow Operations taught by Professor Shubhata Kumar Majumdar. My name is Nagvan Kumar. I'm the teaching assistant for this course. So last week, this is on week 10, we have discussed about the compressible flow, which includes thermodynamic characteristics of compressible flow, and we also discussed about speed of sound or sonic velocity, and we also studied about dimensionless number called Mach number, and then we also discussed about basic equations of one-dimensional compressible flow. So this week, it is on week 11, we'll be discussing about measurement of flow, how it is done, and what are the different instruments or equipments that we have to measure a flow. Okay, so but before looking at different equipments that we need for that we'll be using for measuring a flow, we need to understand what are the different type of flows that we have. Okay, so first let's see different type of flows or the flow classification. Flow classification. So it is divided into two types. There is open channel flow, and the second one is closed conduct flow. Okay, examples of open channel flow are flow in water canals, vented pipe walls like drains, sewers, okay, which is like completely open. So these are type of flows where fluid does not occupy the whole cross section of the canal or pipe. Okay, so example, first let me write down fluid does not occupy the whole cross section of the canal or pipe. Okay, so examples flow in channel, or sorry, flow in canals or vented pipelines. So which are like drains or sewers. Okay, the second type is closed conduct flow. Okay, so examples flow of water in pipelines. Okay, flow in water supply pipes or district heating pipes. Okay, so these are the examples of closed conduct flow. Okay, so let's first understand open channel flows, then we'll go to closed conduct flows. So in this type of flow, that is in open channel flow, in open channel flow, we the stream or the water stream or whatever liquid it is flowing, so it will be having a free or unconstrained surface open to the atmosphere. Okay, so force of gravity and also the force of gravity relative to inertia on the fluid causes the flow, and the progressive fall or decrease in water surface elevation occurs as a flow moves downstream. Okay, so let me write down the points as well. So flowing stream has a free surface. free or unconstrained surface open to the atmosphere. Okay. And force of gravity is relative to the inertia on the fluid, and this causes the motion. Force of gravity relative to inertia on the fluid causes the flow. Okay. So the increase and decrease in water levels or water elevations will cause the will occur as the flow moves downstream. Okay. A progressive fall or decrease in the water surface elevation occurs, just a second, as the flow moves downstream. Okay. So, and other parameters like surface tension, viscosity. So, these are the governing factors for progressive fall or decrease in the flow rate. Okay. So, these are the parameters which will govern the progressive fall or decrease in the flow rate. Surface tension and viscosity. Okay. So, these are the parameters. And depending upon the effect of viscosity relative to inertia, so which is represented by Reynolds number. Okay. So the flow can be either laminar or turbulent, and it can also be a translucent flow, which is in between turbulent and laminar flow. Okay. So depending upon the Reynolds number, the regime of flow is determined. Okay. So whether it is laminar flow or turbulent flow or transitional flow. Okay. So now coming to the second type, that is closed conduct flow, or we can also say closed channel flow. Okay. So the flow in these closed channels is basically caused because of the pressure difference. Okay. So let's say you have a channel here or a closed conduct here. So the flow happening inside these contacts is because of the pressure difference across the length of the pipe or channel. Okay. Flow is caused by a pressure difference in the conduct. And the flow rate will depend upon four parameters. So if you increase the pressure drop or if you increase the pressure difference, what will happen? You are providing more driving force, right? So if you're providing more driving force, then automatically flow rate will increase. So that is going to be the first parameter which will be affecting the flow rate. That is pressure difference between the ends. Okay. And let's say you're applying, for example, let's say you're applying 10 Newton pressure difference across a length of, say, again 10 meters. Okay. And there's one more case where you're applying the same pressure difference across a length of 100 meters. Okay. So how would the flow rate vary? So in the second case, the flow rate will be less, right? Because it is getting diluted over a large length. Okay. So that is why distance is also one important parameter which will determine the flow rate. Distance between the ends. Okay. And we also know that Q is equal to VA, right? That is, flow rate is equal to velocity into area. Okay. So if you are increasing the velocity, what happens to the flow rate, or what happens to the, and this should be constant, right? Okay. So if you are increasing the velocity, so I'll write it down. VA is equal to some K or uh, constant. Okay. So if you are increasing the value of A, that is area of cross section, V will automatically decrease, right? Okay. Or let's say in this case, if you are changing the value of A, Q will also vary automatically, right? Okay. So area is also one parameter which will influence the rate of flow rate, area of the conduct. Okay. And are there, what is the fourth parameter that is going to affect? So we have roughness. Okay. So which is the property again. Okay. And it also depends upon the bends. Okay. If there are more bends, flow rate will again decrease, right? Because when there are more bends in the pipe, it will offer more resistance to the flow rate. Okay. Every time, let's say a pipeline is of something like this. Okay. So every time when the fluid is flowing in these pipelines, every time when it comes across these bends or joints, it has to lose some energy in order to cross these joints, right? Okay. It has to change its direction, right? So it will lose, obviously lose some energy here. Okay. So all these properties combinedly, we can say hydraulic properties of the conduct. So all these parameters will also be affecting the flow rate. Hydraulic properties of the conduct. So what are those parameters? Shape, roughness, and bends. Okay, so you can also call this as restrictions. Okay, so these are the four parameters which will affect the flow rate of a fluid in a closed channel pipe, closed channel or closed conduct. Okay, so now let's see what are the different type of flow meters that we have to measure the flow rate. Classification of flow meters. Okay, so based on the working principle, flow measuring devices can be classified into different types. So this is based on working principle. Okay, the first one is differential pressure flow meters. Second one is variable area flow meters or drag driven flow meters. Then we have positive displacement flow meters. Then we have mass flow meters, and finally we have flow meters, which are used for open channel flows. So let's write them under one classification for open channel. So they are wares, flumes, submerged orifice. Okay, then we also have current meters. We also have acoustic flows, acoustic flow meters, okay, and many more meters for open channels. Okay, so these are the different type of flow meters that we have based on classifications, based on working principles. Okay, so let's try to understand each flow meter in detail. So first, let's understand differential flow meters. Or differential pressure flow meters. Okay, so in these type of flow meters or using these type of flow meters, we'll be measuring the flow by the pressure drop across the obstructions. Okay, okay, let me write it down. The flow is calculated by measuring the pressure drop over an obstructions inserted in the flow. Okay, so the pressure, the flow rate will be measured with the help of a with the help or the pressure, the flow rate will be measured by measuring the pressure drop across the obstructions that are inserted in the flow. Okay, so the differential flow meter is based on the Bernoulli's equation, where pressure drop and the further measured signals is a function of square root of this flow velocity. Okay, so it works on Bernoulli equation, where pressure drop and further measured signal is a function of the square of the flow velocity. Okay, so there are many types of differential flow meters. So let me write down each type. So we have venturi meter, then we have flow nozzle, pitot tube, orifice meter, and we have. So as these flow meters works on the principle of Bernoulli's equation, so let's try to have a recap of Bernoulli's equation as well. So we'll use this for uniform flow. So for an incompressible fluid, so what is an incompressible fluid? Density will be constant, right? So for an incompressible fluid, what is the Bernoulli's equation? V square by 2 plus P by rho plus Gz is equal to constant, right? So let's multiply both the terms, or let's multiply each term with density, that is rho. So let's say this is equation 1. So if you multiply them, we'll be getting rho V square by 2 plus P plus rho G Z is equal to constant. Okay, so this is equation number 2. Okay, so you can also do one thing. So you can divide this equation by G. So if you divide this equation by G, 1 by G. So it becomes V square by 2G plus P by rho G plus Z is equal to H, which is equal to again constant. Okay. So this is a velocity head. This becomes pressure head. This is the potential head. And this becomes the total head. Right? So let's do it for the real fluid as well. Okay. So for real fluid, that means there will be certain non-idealities. Okay, so here we are assuming that it is incompressible flow, it is a uniform flow, right? So in real cases, what happens across a large cross-section area, velocity distribution is not uniform. Okay, and the kinetic energy per unit weight of the fluid transferred across the section is greater than the calculated kinetic energy used by average KE or average velocity. Okay. So in that case, we need to find the true kinetic energy per unit weight. So it will be done by using the equation, binary equation for non-uniform flow. Okay. So K true will be alpha times V square by 2G. That is equation number 4. Okay. So this alpha is called kinetic energy correction factor. Kinetic energy correction factor. Okay. So alpha can be between 1.5 0.03 to 1.06 for turbulent flow, and alpha will be 2 for laminar flow. Okay. So if you take this correction into account, our Bernoulli's equation will become, takes the following form. So it will become alpha into V1 square by 2g plus P1 by rho g plus Z1, which is equal to alpha into V2 square by 2g plus P2 by rho g plus Z2. This becomes equation number 5. Okay. So now let's understand the first differential pressure flow meter, that is Venturi meter. Okay. So it is a device where a flow rate in a pipeline is measured by a narrow part of a tube. Okay. So let me first draw the Venturi meter. So let's say this is a pipe. There will be a narrow cross section. Then okay. So this is the extinction part. Okay. So here we will be attaching a manometer. So you must be knowing manometer, right? Which we've already studied. It is a pressure measuring device. So we'll insert a manometer here. Okay. So let's say this is the fluid inside manometer, and so this is the reference level, and this is the center of pipe. Flow is in this direction. Okay, so let's say pressure is P1 here, and at this location, let's say this is P2, and this is the converging section, converging cone, and this is the diverging cone. This is the inlet, and this is the outlet section. Okay, so this is how manometer looks. So let's understand the principle of manometer as well. So in a venturi meter, sorry, let's understand the principle of venturimeter as well. So in a venturimeter, the fluid is accelerated to the converging section of angle 15 to 20 degrees with pressure difference. Okay, so the angle, the converging cone, angle of the angle in this converging cone is 15 to 20 degrees, and the fluid will be accelerated through this section with a pressure difference. Okay, so obviously fluid will be accelerated because the area is changing, right? So if area changes, if area is decreasing, velocity will increase, right? Okay, because Q is equal to V into A. Okay, so VA will be constant. So if area is reducing, V will increase, right? Okay, so as area is decreasing, velocity will increase or the fluid is accelerated. Okay, so the fluid slows down in the cone with a smaller angle, that is 5 to 7 degrees, where most of the kinetic energy is converted back into the pressure energy. So because of the cone and the gradual reduction in the area, so here there is no vena contracta and the flow rate is at a minimum at the throat. Okay. So high pressure and energy recovery makes the venturimeter suitable for applications where only small pressure heads are available. Okay. So if there's this equipment or the venturimeter, it will be allowing only small pressure drops, or let's say it recovers most of the energy. Okay, during this operation, it recovers most of the energy. So that is why it is helpful, or it is used in operations where there is only small pressure difference or small pressure head is available. Okay, so it may be fitted with any position. Okay, so it can be either a horizontal connection, it can be a vertical connection, or a inclined connection as well. Okay, so but it generally is a but whenever we are using in general applications, it is a horizontal connection. Okay, so it should also be remembered that the venturimeter must run full, and it should be preceded by a tight length of a pipe of at least 5 to 10 diameters, 5 to 10 diameter of pipe to reduce any turbulence inside the pipeline. Okay. So commonly the diameter of throat is kept around 1.5, sorry, zero point 0.5 of the inlet diameter, or one third to three-fourth of the outlet pipe diameter. Okay. So let's apply, as these equipments will work on Bernoulli's equation. Let's apply Bernoulli's equation to this venturimeter and see how we'll be able to calculate the flow rate. So from Bernoulli's equation, okay. So let me just draw it again. So we have a converging section and a diverging section. So here we are attaching a manometer, right? Okay. So let's consider these 2 points which are at a same height. This is P1 and this is P2. Okay. So let's apply there. So this is first point and this is second point. So if you apply Bernoulli's equation here, it will become P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. So what is the equation number? This is equation number 6. Okay. And we also know that V1 A1 is equal to V2 A2, right? Because this is again equal to Q. Okay. So from this equation, let's write V1 is equal to V2 into A2 by A1. Okay. So this is equation number 7. So as they're at equal height, Z1 becomes Z2, right? Okay. So these two get cancelled out. So what are we left with? So if you just change these, if you bring like terms to one side and other terms to the other side, so we will be getting V2 square minus V1 square by 2g will be equal to P1 minus P2 by rho g, right? So P1 minus P2 by rho g will be equal to HP. Okay. So I'll come to that again. So let's get back to this equation again. Okay. And substitute this in this equation. So we'll be getting V2 as 1 by, I'm directly writing a simplified equation. V2 as 1 by square root of 1 minus A2 by A1, A2 by A1 whole square into square root of 2g into P1 minus P2 by rho g. Okay. And what is the formula for Q? That is V2 into A2, right? Okay. So just substitute V2 here. We'll be getting A2 by square root of 1 minus A2 by A1 whole square, okay, into square root of 2g. So let's write this as HP, okay, which is pressure head, okay. So this here, okay. So now let's take this equation here. So this again will be equal to H into gamma m minus gamma m by gamma w minus 1, okay. So let's say this equation number 9, this is 8, and yeah, this is 7, okay. So now Q will be equal to C into A2 by square root of 1 minus A2 by A1 whole square into square root of 2G into HP. Okay, let's say this equation number 10. Okay. So here C is the coefficient of discharge. Okay. So this will give us the flow rate. Okay. So let's look at something called pressure recovery. So here there is a converging section and also a diverging section, right? So that means there will be obviously pressure change in both the sections. Like whenever it is entering into the converging section, there will be pressure difference, and whenever it is coming out or whenever it is going through the diverging section, there'll also be this pressure difference, pressure change, right? So let's see how well this equipment is, or let's see how good this particular fluorimeter is in recovering the pressure difference, pressure. Okay, because so let's say this is the initial, let's say here we are having P1 pressure, and let's say if this pressure is lost during this compression and expansion, okay, that means you are losing energy, right? So that should not happen. So let's see how well this recovers the pressure. So let me draw a graph here. Permanent pressure drop or percentage of maximum pressure drop. Okay, and this is section opening percentage of pipe. Okay, so after, and this is for venturi, this is for nozzle, and this is for orifice. Okay, so after the difference has been generated in the differential pressure flow meters, the fluid passes through the pressure recovery exit section, right? That is the diverging section. So where the differential pressure generated at constructed area is partially recovered. Okay, so the pressure drop in orifice plates are significantly higher than in venturi tubes. Okay, so after the constructed area, that is the converging section, the fluid is passed to the recovery section, which is again diverging section. Up to 80% of the differential pressure generated is up to 80% of the differential pressure generated at the converging section or constricted area is recovered. Okay, up to 80% recovery is possible. So What are the advantages of venturimeter? Advantages of venturimeter. So there's a less chance of getting clogged with sediments. Okay, that is one advantage. Because if it is getting clogged, you have to again, open it and then clean it, right? So that is an advantage here because there is less chances of getting clogged with sediments. Then coefficient of discharge is very high in this equipment. Coefficient of discharge is very high. It its behavior can be predicted easily, so that is also an advantage. Okay, so it can be installed vertically, horizontally, or in inclined position. So that is also an advantage. And they are more accurate and can be used for a wide range of flow rates. Okay. And the final advantage is that around 80% of the pressure drop can be recovered, which is a good thing. Around 90% of pressure drop can be recovered. Okay. So obviously there will also be disadvantages, right? So what are the disadvantages of a venturi meter? So they are large in size and therefore space if the space is limited, they cannot be used. Okay. They are large in size and hence where space is limited, they cannot be used. Okay. So and also this is an expensive equipment, so expensive initial cost, installation and maintenance also required. What is the disadvantage? Expensive initial cost, installation and maintenance. So requires long laying length. That is, the venturimeter has to be preceded by a straight pipeline which is free from fittings and misalignements. Okay, to avoid any turbulence in the flow. Okay, so you'll be requiring a long laying length. Required long laying length. That is, the venturi meter has to be preceded by a straight pipe which is free from fittings and misalignments to avoid turbulence in flow. So this is done for satisfactory operation. Okay. And this cannot be used in pipelines below 2.5 centimeter in diameter. What is a disadvantage? Cannot be used in pipes below 7.5 centimeter dia. Okay. And then the next disadvantage is maintenance is not easy. Then cannot be altered for measuring pressure beyond a maximum velocity. Maximum velocity. So these are also disadvantages of venturi meter. Okay. So let's take an example and let's see how we'll be able to use this venturi meter. Okay. So calculate the flow of water flowing through a 40 into 15 centimeter horizontal venturi meter where differential gauge connected to the inlet end of the meter and its throat shows 2.25 centimeters Hg. Assume coefficient of discharge as 0.98. Okay. So let me just write down the question first and then we'll solve the problem. Okay. Calculate the flow of water flowing through a 40 into 15 centimeter horizontal venturi meter in the differential gauge connected to the inlet end of the meter and its throat shows 25 centimeters Hg. Assume the coefficient of discharge is 0.98. Okay. So, okay. So A1 is 0.1256 meter square and A2 is 0.01765 meter square. Okay. So this is not given. So sorry, this is also given data. So okay. So first let's calculate HP. That is what is the formula for HP? Hp is equal to H into gamma m by gamma w minus 1. Okay, so Hp will be equal to H into gamma m by gamma w minus 1. Okay, so this is nothing but Hp is equal to, what is the value of H? That is height difference, 25 centimeters. So if you convert this into meters, it is 0.25. What is gamma m? It is nothing but density of mercury. Okay, so it is 3600 by, now what is density of water? That is 1000 minus 1. Okay, so this will give us 3.15 meters of fluid flowing. Okay, so in this case it is water, 13.15. Okay, so from this we can calculate Q, right? So Q will be equal to C into A2 by square root of 1 minus A2 by A1 whole square into square root of 2G into HP. So if you substitute all the values, C is also given, this coefficient of discharge as 0.98, right? So A2 is given, A1 is given, G we know, HP we have calculated it. So if you substitute all the values and if you do the calculation correctly, you'll be getting this as 0.137 meter cube per second. Okay. So this is how we will be able to calculate flow rates. Okay. So we are done with venturimeter. So now let's study pitot tube. Okay. So in early 18th century, pitot. So Pitot is a scientist. Henry D. Pitot is a France civil engineer. So in 18th century, early 18th century, he procured a simple measuring device of flow rate. So it was made by bending a glass tube by 90 degrees at its lower end. So this is simple measuring. So this is simple device for measuring flow rate of a fluid. Okay, so this looks something like this. So it will be something like this. Okay, so this you'll be placing it in a stream of water, and then you'll be able to calculate the flow rate of water. Okay, so whenever you're placing this tube in water, or let's say in any flow, what happens? So the flow, okay, the flow, or let's say the water in the tube will go up. Okay, so the height of water will increase. Okay, and the height of water will help you in determining the velocity of the fluid. Okay, so he measured the flow velocity by measuring the increased height of water due to the pressure. Okay, so and he did this experiment, the first experiment in a river, see carrying a glass tube with a bent end. Okay, so let's see how we'll be fixing this in a actual flow. So let's say this is a pipe. So let's say this is the height of water column in the second tube. This is density rho. This is point B. This is C, and this is A. Okay. So the tube is so designed that a streamline end, a hole by the name B is opened in the face of a flow. So while another hole C in the direction of vertical to the flow is used in order to pick out separate pressures. Okay, so here PA is this is again static pressure. Okay, so we'll be able to find out static pressure, dynamic pressure. So let's see how we'll be using it. So again, this is also a pressure, differential pressure equipment, right? This is a differential pressure flow meter, right? So this also works on Bernoulli's principle. So let's apply Bernoulli's principle at A and B. Okay, so we'll be getting PA by rho g plus VA square by 2g is equal to PB by rho g. Okay, so this gives us PB minus, so this gives us V is equal to square root of 2 into PB minus PC by rho. Okay, so let's say PB by PB minus PC by rho g as HP. So that means VA will become square root of 2G H. Okay, so with an actual pitot tube, since some losses occur due to its shape and fluid viscosity, the equation is modified as VA is equal to CV into square root of 2G H. Okay, so we know that because of the bends, there will always be pressure loss, right? So that is why we added something called CV. This is a coefficient of velocity pitot tube coefficient. Okay, okay. So let's also understand Prandtl tube. Okay. So pitot static tubes, which is also known as Prandtl tubes, are used as aircraft speedometers. So the actual tube on aircraft will be around 10 to 15, sorry, 10 inches. So which is around 25 centimeters long. Let me show how it works. Okay. Sorry for this. So you have some bulb here, okay, and you have one more tube to measure static pressure. Okay. So these are the tubes which will help in measuring the speed of the aircraft. Okay, so these are the vital equipments which will help in measuring the speed of a aircraft. Okay, so there'll be three sets, I guess, three sets of Prandtl tubes to measure the Prandtl or pitot static tubes to measure the flow rate of a, sorry, to measure the speed of aircraft. Okay, so coming to practical limitations of use of pitot tubes, if the velocity is low, the pressure difference is very small, right? And it becomes hard to accurately measure with a transducer. So errors in equipment could be greater than the measurement. So pitot static tubes won't work well when the velocities are very low. Okay, but whereas in aircraft it will be flowing at high speeds, right? So there is no issue with that. But whenever the velocity is very low, using pitot tubes will not be a good option. Okay, so if velocity is very high, okay, so that means if it is a supersonic velocity, so it violated the assumptions of Bernoulli's equation, and measurement will also be again wrong. Okay, so at the front of a tube, a shock wave appears that will change the total pressure. Okay, so then you'll be needing corrections for shock wave that can be applied to allow it for high speed craft or high speed aircrafts. Okay, so if the tubes becomes clogged or pinched, so the resulting pressure at the transducer or not the total and static pressures of the external flow. Okay, so the transducer output is then used to calculate a velocity that is not the actual velocity of the flow. Okay, so these are the issues that we have with pitot tubes. One, we cannot use it when the velocity is low. Second, we cannot use it when the velocity is very high. This is in supersonic flow, and you can also we should also be careful not to clog or pinch the pitot tubes. So if that happens, it will not be taking the accurate flow rate, or it will not be calculating the accurate pressure. So in turn, it will also give you a false velocity. Okay. So let's solve one problem related to this pitot tube. A submarine moves horizontally in sea and has its axis 15 meters below the surface of water. A pitot tube properly placed just in front of the submarine and along its axis is connected to the two limbs of the U tube manometer containing mercury. The difference of the mercury level is found to be 17 centimeters. What is the speed of the submarine? The density of the seawater is 1.026 with respect to normal water. Okay. So we are supposed to calculate the speed of a submarine. Okay. So we have this equation P1 minus P2 by rho g is equal to HP, right? Which is equal to H into gamma m by gamma W. Okay. So we were given a value of H, that is 0.117 centimeters, right? Height of mercury, that is 0.17 into, so it is given here. Okay. And what is the value of gamma mercury? It is 13.6, and gamma water is 1. Okay. So here we were given density of salt seawater, just to confuse us, so don't get confused. So density of water is 1. So this will give us 2.081. Okay. So VA will be equal to square root of 2G into HP, which again is equal to, if we substitute all these values, you should be getting 6.391 meter per second, which is also 23 kilometer per hour. Okay. So now let's understand. So we were done with venturi meter, then pitot tube. So now let's understand orifice meter. Okay. So do you have any doubts until now? If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. Any doubts? So this device is a cheaper device when compared to a venturi meter, and this also works on the same principle of a venturi meter. Okay. So let's directly apply Bernoulli's equation, as this is also a pressure differential pressure equipment. So let's directly apply Bernoulli's equation. So these are the pressure tapping the holes. Then we also have lower section. Okay. So these are the streamlines. Because of these obstructions, there will be change in the streamline. Okay, so this is the central line or the middle part. So let's say this is point 1 and this is point 2. Okay, so let's apply Bernoulli's equation at point 1 and 2. So first we need to assume that the particles which pass section 1 is also passed section 2. Okay, so then Bernoulli's equation will become V1 square by 2g plus P1 by rho g plus Z1 is equal to V2 square by 2g V2 square by 2g plus P2 by rho g plus Z2. Okay, so as the pipe is horizontal, Z1 will be equal to Z2, right? Z1 will equal to Z2. Okay, so these two gets cancelled out. So then we'll be left with P1 by P1 minus P2 by rho g will be equal to V2 square minus V1 square by 2g. Okay, so V2 will be equal to square root of 2g h plus V1 square, right? So from here, let's also write this as HP, which is equal to P1 minus P2 by rho g. That is pressure difference between difference of pressure heads at P at location 1 and 2. Okay, so let A not be the area of orifice. So coefficient of contraction is given by CC, which will be equal to A2 by A naught. So here A naught will be greater than A2. Okay. So again from continuity equation, by applying it at equation at section 1 and 2, we can write at section 1 and 2, we can write A1 V1 is equal to A2 V2, right? So we can write V1 as CC into A naught into V2 by A1. Okay, so just use this equation. So from here we can write V2 as square root of 2g HP plus C square into A naught square into V2 square by A1. Okay, we can also write V2 as square root of 2g HP by square root of 1 minus A naught square by A1 square into CC square. Okay, so the expression is ideal is for ideal condition and is known as theoretical discharge. Okay, so Q will be equal to A2 into V2, which is again V2 into A naught into CC. Okay, so this will give us A naught into CC into square root of 2g HP by square root of 1 minus a naught square by a1 square into cc square. Okay. So if CD is the coefficient of discharge for orifice meter, so then CD can be defined as cc by square root of 1 minus a naught square by a1 square into cc square. Okay. So finally we can write discharge as q is equal to cd into a naught a1 into square root of 2g hp by square root of a1 square minus a naught square. Okay. So the coefficient of discharge of orifice meter will be much smaller than that of a venturi meter. Okay. So this has to be noted down. Always remember that coefficient of discharge of the orifice meter is much smaller than that of a venturi meter. Okay. So now what are the advantages and disadvantages of orifice meter? First, let's see advantages of orifice meter. Okay. So it measures a wide range of flow rates. So this is a simple construction equipment. So it has simple construction or design. So RFEs are small plates and they can be easily installed or removed. RFEs are small plates and easy to install or remove. Orifice or it also offers very little pressure drop of which 60 to 65% is recovered. Offer very little pressure drop of which 60% to 65% is recovered. Okay. And orifice meters can be easily maintained. Okay. And they are more suitable for gases and liquids, most of the gas and liquids. And they are also inexpensive. Okay. So these are the advantages of an orifice meter. Okay. So what are the disadvantages of orifice meter? What are the disadvantages of orifice meter? It requires homogeneous axial single fluid flow. Okay, and their accuracy is affected by density, pressure, and viscosity. Viscosity of fluid viscosity limits its pressure measuring range, requires tight pipe run to ensure accuracy is maintained. And then pipeline must be fully, especially for liquid flow measurements. So it should be completely filled. They have low range availability. They have low range ability. Okay. So these are the disadvantages of Venturi, sorry, orifice meter. Okay. So do you have any doubts until now? Any doubts? If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. If not, we'll directly move on to the problem solving session. Okay, because we are running out of time. So there are many other equipments that we need to discuss, which are already discussed in the class. Okay, so if you have any doubts, even in the equipments which are or in the theory which was discussed in the class by professor, or in the problems that you might have solved, so you can ask me and I'll try to answer them. You can unmute yourself and ask me, or post them in the chat box as well. I'll try to answer them. If not, we'll directly move on to the problems part. Okay, so if you don't have any doubts, then let's move on to the problems part. So coming to the first question. In case of a closed channel flow, the flow rate depends mainly on the pressure difference between the ends, distance between the ends, the area, and hydraulic properties of the conduct. So this was discussed in the first slide, I guess. So which parameters or which factors will influence the flow rate of a closed channel flow, a flow rate in a closed channel flow? A pressure difference will affect the flow rate. Distance between the ends will also affect the flow rate. Area and hydraulic properties of the conduct will also affect. So it is option D. That is all the above. So all these parameters will be affecting the flow rate in a closed channel, right? So the differential pressure flow meter is based on Bernoulli's equation, Pascal's equation, Prandtl equation, all the above. So the differential equation is based on the Bernoulli's equation. Okay, option A. So coming to third question, for a laminar flow, so for a laminar flow, alpha will be equal to 2. Okay, so for a laminar flow, the kinetic energy per unit weight can be expressed as, so this is in the true kinetic energy per unit weight can be expressed as Ke2 is equal to V square by G, Ke2 is equal to V cube by G, Ke square is equal to V square by 2G, none of the above. So the answer would be Ke. So what is the formula for Ke? V square by 2G, right? So Ke true will be alpha into V square by 2G. So for laminar flow, alpha is equal to 2, right? So if you substitute that, Ke true becomes 2 into V square by 2G. So 2 gets cancelled out. So Ke true will be equal to V square by G. So that is option A, right? So coming to third question, a submarine is moving 20 meters below the surface of the water. A pitot tube containing mercury with density 13.56 is showing the difference of a mercury level of 22 centimeters. What is the speed of submarine? The density of seawater is 1.030 with respect to normal water. So we were given a few points. Let me just write these points down or write the data down. So we were told that density of mercury is equal to 13.56 and H is equal to 0.22 meters. So it was given in centimeters. So let me write down in 22 centimeters, which is equal to 0.22 centimeter, 0.22 meters. Okay, and we are asked to calculate the speed of submarine. So how do we do it? So we have already done this. So can someone tell me how to calculate the speed of a submarine using the following data? So HP will be equal to P1 minus P2 by rho G, right? Which again is equal to H into gamma M by gamma W, right? So H is already given, that is 0.22. This is 13.6, that is density of mercury by density of water 1. So what will be the value for this? 13.6 into 0.22. So it will give us 2.992. Okay. And what is VA? VA is nothing but square root of 2G into HP, which is equal to 2 into square 9.8 into 2.992. So what will be the answer? What will be the answer? So this will give us something like 7.65, I guess, meter per second. Okay. So this is 7.54. Okay. So maybe some calculation. So if you just round it off and then substitute, you'll be getting 7.54. Okay. This is option A. So coming to the fourth question, the actual velocity in a contracted section of jet of liquid flowing from a point zero 0.05 mm, point zero 0.05 meter diameter orifice is 12.7 meter per second under a head of 10. What is the value of coefficient of velocity? So this is related to orifice. Okay. How do you do it? We were asked to calculate coefficient of velocity. How do you calculate it? How do you calculate it? So we were given actual velocity in a contracted section, that is in the converging section, that is 12.7 meter per second. Okay. So we are also given diameter, so we can calculate area, right? Okay. So we have area, we have velocity, we also have head. Okay. So will we be able to calculate coefficient of velocity? How do you do it? It could be wrong. Just what is your thought on this? Like, how do you solve it? How do you plan to solve this? You can type it in the chat box as well if you don't want to speak up. You can type it in the chat box as well. How do you calculate it? Okay, then I'll leave this problem. Try to solve it. And if you have any doubts, then ask me. Okay. Or if you're stuck somewhere, then ask me. I'll try to help you. Okay. So coming to fifth question, what is the flow rate of water flowing through a 40 into 15 horizontal venturi meter when the differential gauge connected to the inlet end of the meter and its float is shows 25 centimeter Hg. Assume the coefficient of discharge is 0.98. So we already solved this problem, right? In the first part, that is when we were discussing venturi meter, we solved the same problem, right? So answer, if you solve it correctly, it will be 0.137. Okay, so try to solve it. We've already solved the same problem. Okay, so coming to sixth question, a venturimeter can recover around 60% of pressure drop, 90% of pressure drop, 40% of pressure drop, none of the above. So venturimeter can recover around 90% of the pressure drop. So which is option B. Okay. So coming to seventh question, the venturimeter is suitable where only small pressure heads are available due to its high pressure recovery, high energy recovery, both A and B. Option D, none of the above. So venturimeter can be used even in cases of small pressure heads. This is because it has both the advantage, that is high pressure recovery and also high energy recovery. So that is why it is able, that is why we are able to use venturimeter even in areas where small pressure head is available. So coming to eighth question, in a lobe impeller meter, the volumetric flow rate is calculated by number of revolutions of the rotameter, pressure difference between ends, velocity difference between ends, none of the above. So it is number of revolutions of the rotors. Option A. Okay. So coming to ninth question, an example of variable area flow meter is venturimeter. Option B, rotameter. Option C, flow nozzle. Option D, orifice meter. So which of these is a variable flow meter? It is rotameter, right? Option B. Okay. So coming to 10th question, the relation between the angular velocities of the turbine rotor to the fluid velocities flowing through the turbine is option A directly proportional to each other, option B inversely proportional to each other, option C either A or B, option D none of the above. That is, third answer would be directly proportional to each other. That is option A. Okay. So coming to 11th question, in a rotameter, the float rises until there is a state of dynamic equilibrium between upward differential pressure, buoyancy factors, with which of the following? Option A, inertial forces, option B, shear forces, option C, gravity forces, gravity factors, option D, none of the above. So, what is the correct answer? That is gravity factors. Option C. Okay. So, coming to 12th question, the flow nozzle working is similar to which of the following? Option A, pitot tube, option B, rotary venometer with more than three components, venturi meter without its divergent cone, option D, turbine meter with axial suspension of rotor. So correct answer is venturi meter without its divergent cone. Okay, option C. So all these concepts were discussed in class. So principle of one Kalman effect is employed in which flow meter? Option A, turbine, option B, Doppler, option C, vortex, option D, all of the above. So it is employed in vortex type flow meter studies, option C, right? Coming to 14th question, Doppler and transient time flow meters are two types of which flow meter? Option A, Venturi meter, option B, Doppler, option C, lobed impeller, option D, electromagnetic. Which of this following is correct? Anyone? You can just type it in the chat box as well. What is the correct answer? And directly then the answer is option B, Doppler effect, Doppler flow meter. Okay. So coming to 15th question, calorimeter, calorimetric flow meter is based on the principle of temperature. Option A, temperature difference between heating element and the outer body shell. Option B, temperature difference between heating element and the medium in the pipe. Option C, temperature difference between heating element and outer nozzle casing. Option D, none of the above. So calorie flow meter works on the principle of temperature difference between heating element and medium in the pipe, right? Option B. Okay. Okay. So if you have any doubts, you can ask me, or you can post them in the chat box, or unmute yourself and ask me. If not, we can end this session. So before we end the session, so we'll be having one more class on Tuesday. Okay, so we'll try to have a recap of everything first. Okay, so like there's an extra session on Monday, sorry, Tuesday. So on Tuesday from 2 o'clock, I guess, there'll be an extra session. So where we'll try to have a recap of everything that we have studied until now. Okay, and then we'll conclude it by maybe 4 o'clock. And after that, we have again same session, our regular session at 6 o'clock from 6 to 8. Okay, where we'll try to finish the last week of this course, that is week 12. So that's the extra session was supposed to happen after the class of week 12, but because of lack of time, we are having it before week 12 class. Okay, so that is why extra class will be from 2 to 4, and then week 12 class, that is our regular class, will be from 6 to 8. Okay, so that means next Friday, next Tuesday, we will be having two sessions. Okay, one in the afternoon from 2 to 4, and the other one is our regular session from 6 to 8. Okay. So, if you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. If not, we can end the session. Okay. So, thank you everyone. Thank you for attending the session. Let's meet on next Tuesday. Thank you.